So, hello everyone. Welcome to this third season of the Good Vibrations seminar series. I'm very happy to start this new season tonight with you, with Jeroen Audernaert from KU Leuven. Just before I give the floor to Dominic so that he introduces him, I just would like to announce that we have a very rich and diverse set of speakers this year. I'm very happy that some slots are taken by people who are from overseas, so we are able to offer some talks at different times of the day, as you can see with tonight. Anyway, you can check it out on our website and see the whole season is announced there. So thanks a lot, Jeroen, for having accepted to give this first seminar of the third season. And Dominic, the floor is yours.
Yes, so it's my pleasure to present Jeroen Audernaert to give the first opening talk of season 3 of Good Vibrations. And Jeroen is a PhD student who's under the supervision of Connie Ertz and Andrew Tchenko at KU Leuven. He's in his final year now, so I'm not worried about him writing his thesis, but he has to do it at some point. But he is someone that you should know because he's one of the leaders of the TADAR working group within the TESS Astroseismic Consortium and has done some fantastic work in the classification of pulsating and variable stars in general. So Jeroen has a little bit more work to do before he finishes his PhD, and we're going to learn about some of his exciting results today. So over to you, Jeroen.
Well, thank you very much for that nice introduction, Dominic. So yeah, first of all, thanks to the audience for being here, especially given that it's already 10 o'clock in Europe in the evening. And today I will talk about actually how we can use artificial intelligence and machine learning specifically to actually gain new insights in astronomy and in particular for TESS data and Kepler data. So I will talk about how we can discover new sets of pulsating stars such as Delta Scuti and Gamma Dor stars and their hybrid pulsators with machine learning, and how we can actually use the machine learning techniques in this case to also probe the physics of these stars in an automated way, so that we can actually gain new physical insights on this. Now, before actually diving into the astronomy part, I will give a high-level overview of artificial intelligence, because it's nice, like I'm talking about, mostly I just talk about how we use machine learning to classify all the stars, but it's better if I first give a nice overview of that. So artificial intelligence actually consists of a lot of different topics, and it's more high level. So AI techniques or any technique that actually enables computers or systems to solve a task in a way like humans do. And this can be, for example, this can involve robotics or also like data representation. So one of the key items in AI is just how do we represent knowledge, for example, how do we represent physics? And machine learning is only one small part of this. And for machine learning, we specifically need a lot of data. So machine learning is a subfield of AI, and here we really need need a lot of data to actually train algorithms to then give us predictions. So machine learning is very heavy on data, and we learn all of it, while AI can actually be involved, not necessarily has to involve a lot of data, can also be probabilistic assignments or just knowledge representation in general. And neural networks and deep learning, those are topics that you see a lot nowadays in papers as well appearing on the archive. Those are some type of brain-inspired machine learning models that try to learn a lot of weights and make complex relationships between the different type of input and output variables. And deep learning is just a more complex version of neural networks. Now, within machine learning, we can actually distinguish between two high-level classes of learning, and that is supervised learning and unsupervised learning. And I will actually talk about both of these types of learning today and their applications in astronomy. So for supervised learning, what we do here, in case we take some images, for example, we give the machine learning algorithm all the images, and we also provide a label with them. So we say that the image on the top left is a cat and the one next to it is a dog. And then we keep on providing all these different examples to actually train the parameters of the model. And then the goal is to actually afterwards give an image, for example, of a dog, to the machine learning algorithm, and so that it's actually able to predict that this image is a dog. Unsupervised learning, on the other hand, doesn't need any table. So it tries to look at the common characteristics of the data and tries to find a natural structure of the data space, and therefore find the clusters that are present in there. In case we would have some labels, then we can do something that is called semi-supervised learning. And here we also look at the structure of the data space, and we can see that there are different clusters. And if we then just have, for example, one label of a cat, we could extrapolate that to the whole cluster. And we could say that most likely all the examples in this cluster are cats. And then the other, if we would then have one of the other cluster, the green one, we could also say they are dogs, for example. Now, when we take this to astronomy, supervised learning, we would actually give the machine algorithm lots of light curves, for example, of delta Scuti stars, then of gamma Dor stars, and we would then train the algorithm to actually distinguish between these different types of systems. And unsupervised learning, we would just try to represent the light curves in some kind of way, and then look at the data space and try to find the natural clustering of the data, but we would just not necessarily know which type of star is present in each cluster. But it would be very interesting to actually apply this to find new classes of stars that have not previously been discovered, or see how we can actually find certain correlations within the data space. Now, just a brief overview of neural networks. As I said, they are kind of based on the brain. So what we do is we first, in case of an image, we try to build we have a pixel representation, and then the network tries to build more and more high-level representations of the image, such that in the end, it actually comes to the conclusion that it is a cat. And if you look at it graphically, essentially what you have is, for a simple neural network, you just have the input nodes, and then you multiply these with some weights. So to get to some kind of hidden nodes, these weights, so all the arrows you see here, that is what we train with the neural network algorithms. And then we multiply the hidden nodes again with some weights to actually come to the output layers. And when we stack multiple layers, multiple hidden layers, we just get more and more complex networks, and we end up with something that is called deep learning in the end, once we add a lot of those and we increase the number of nodes in each layer as well. In case you would look at it from an image side, you can see here on the left a nice example. So what we essentially do is we take each pixel of the image. So this is the first layer, the input layer. And then in the second layer, the weights actually try to construct some kind of new hidden representation that is still quite simple. In this case, it's just edges. So you would see different colors that look like that kind of belong together, and that can help in discriminating these. In the next one, we build an even higher level representation of actually corners and contours. So you can actually see already something in the representation of this layer. So it tries to detect, the algorithm then tries to detect whether this is what we see or not in the image. To then in the third layer, in the fourth layer, actually see the object parts here, and so we can see whether it's a wheel, whether it's we can see that here there's a wheel represented or a person represented, and then afterwards, once we have these representations, we can actually go to the fact whether it's to actually assign labels to these objects parts or not. And that's kind of the way deep learning works, and it is also a very commonly used technique in machine learning, also in astronomy, because it's so powerful. But it's not the only technique. One of the more simpler ones is our decision trees, so random forest. And here we essentially just try to learn some kind of trees that can easily help us decide which type, based on the input, which type of output we have there. So on the left, you see a very simple example based on whether we want to play tennis or not. So we just give as input, for example, the first variable is the outlook of the weather. So it's either sunny, overcast, or rain. And then we have two more variables. Next one is the humidity. So if it is sunny, and then we look at the humidity, and if it's high, then we don't play tennis. If it's low, then we do play tennis, for example. And we try to leverage this is just a very simple decision tree, so it's not too complex, and it can only represent very simple cases. But what we try to do is combine lots and lots of these decision trees to get to something that is called a random forest. We train multiple decision trees with different random initializations and on subsamples of the data, and then combine the output of all these different decision trees into a new average prediction, for example. And this is then way more powerful than a single decision tree. And this is what we call a random forest. We have other methods as well, such as, for example, gradient boosting machines. And here what we try, they are also based on trees, but each new tree that we trained, for example, tries to correct the mistakes from the previous tree or the ones that is making. So both are very powerful techniques, and the benefit of decision trees is they are not as sensitive to different hyperparameters. So random forests are very easily tunable. I mean, they're very robust and it can easily be applied, while a neural network takes a long time to train and is very sensitive to the parameters. So sometimes it's therefore really easy to actually take a decision tree, and it's still, depending on the case, it actually can provide better results sometimes than neural networks or not, and it's more robust in general and also a bit more easier to generalize. But as said, it really depends on the problem set. Ideally, you can actually combine multiple of these into one algorithm. Now, moving on to light curve classification, now that I've given you a bit of a high-level overview of what machine learning and artificial intelligence is. So as I said, the goal of my thesis project is to actually classify the light curves that are observed by the TESS mission. In order to do this, we actually first started from Kepler data because we already had a large set of labeled light curves available here. Now, the research I did is actually, or part of the research I did is to actually help build the TESS data for astroseismology variability processing pipeline, and specifically the classification part. So what we do for TESS here is we take the photometry, we construct the light curves, then in the next one, we do the correction. So we correct all of these. And then the last part is that's shown here is a classification part. And here we just try to classify each of these different light curves according to their stellar variability types with both supervised methods and unsupervised methods. And that's really the classification part is the part where I'm mostly involved in. Now, here you can see the overview of our stellar variability classification pipeline. So the first step we do is a top level classification. So here we classify each of the light curves according to whether it's a solar-like oscillator, either transiting or eclipsing signal, gamma dor, delta scuti, and so forth. You can see that still some parts are grouped here. For example, gamma Dorstan SPBs are grouped, and same for delta Scuti and beta Cephs, because sometimes it's just very difficult to distinguish them purely based on light curve information only. So therefore, in our top level classification, we only use these high level classes and only use light curve information. In the next classification, we go more into details, and for some of them, we just also add we will also add additional data such as color information, for example, to actually make it more easily distinguish the two classes from each other. What I will here talk about in particular today as well is just the top level classification, and then afterwards I will dive into the cases of gamma Dor stars and delta Scuti stars, and specifically to actually separate them from their hybrid components, and also to show that we can actually find new insights through the machine learning algorithms for them. Now, first, let's start with a supervised high-level classification scheme. So what we do is we take the light curves, and then we do 4 different types of feature classification for 4 different types of classifiers. And each of these 4 classifiers is actually a different type of algorithm. So we, for example, have SLOSH, which is a convolutional neural network, and that is trained on the power spectrum. Then we also have a sorting head. This is a random forest and uses, for example, the first, the second, and the third fundamental frequency. Then we have some entropy metrics that are in there, the skewness, and all sorts of things like that. Then we have another one, which is called a gradient boosting model, also with different feature sets. So the feature sets are actually different in each classifier. And the last one is another random forest, but with different features as well. For example, it uses a self-organizing map, which is some kind of automatic way to actually structure the light curve information. And what's really important when you combine multiple classifiers is that you try to make sure that each of the classifiers that all the classifiers are uncorrelated, so that they don't make the same mistakes. Because if they would make the same mistakes, then it doesn't make sense to combine all the results because it doesn't add any value. While if each one is stronger or weaker in certain parts, for example, it's better at classifying solar-like oscillators or gamma Dor pulsators, and then we combine the output, then we actually get to a very powerful conclusion. And that is what we did here. We took the probabilities from each of these classifiers, so it's 8 probabilistic assignments For example, each classifier gives us 80% probability it's the solar-like, 0.1% that it's a delta Scuti, and 0.01 for all the other classes, for example. So we have 4 times 8 probabilities, and then what we do is we learn a very shallow random forest. So not too many, that doesn't consist of too many decision trees, to actually learn the best way to combine these probabilities from each classifier and come to a new output. So to actually do our general classification. And this is then also a probabilistic one where we get to know whether what the percentage is that a certain light curve belongs to a certain variability class. Now here, just a brief overview of the feature engineering that is used in some of the methods. As I said, we use the amplitude spectrum. In the time domain, we use the skewness and the minimum absolute, the skewness, for example. And then we also have some other ones like the multiscale entropy, which kind of assesses the complexity of the light curve. The exact features, there are too many to list, but those can be found back in the paper in case you're interested in those. Now, the results on these, as I said, we actually trained it on Kepler data first because we had so many labeled light curves available here, where for TESS in the beginning, we did not have those. And so we constructed a training set of about 8,000 or 9,000 stars, and then we trained it on 80% of these and tested it on the remaining 20%. And we got an accuracy of about 94.9%. And you can see the confusion matrix here on the left. And you can actually notice that it really depends on the type of data, on the type of classes. So the performance depends on the type of classes. For gamma dwarf stars, it was a bit lower, about 90%, while for aperiodic stars or solar-like stars, it was 98 and 94%, for example. And on the right side, you see actual examples of each of those different types of light curves. But as I said here, it's only a small set, so it's not so it's based on label data. Afterwards, we also validate on the complete Kepler data set, and we found that the performance was actually similar. So we vetted a random sample of each predicted class, and we came to the conclusion that indeed our average accuracy was something around like 94%, for example, there as well. Now, because we trained on Kepler data, of course, but the ultimate goal is to apply it to TESS data. There are some things that we need to take into account because TESS has actually different instrumental characteristics than Kepler. So a classifier trained on Kepler can maybe not directly be applied to TESS because there might be some differences in instrumental characteristics. And this is also really what we found. For some types of stars, it works great. For example, for delta Scuti stars, the classifier that is trained on Kepler data predicts very nicely, although the data quality is different. But for eclipsing binary systems, for example, TESS has a lot of momentum dumps. So there we see all these drops actually get classified as binary systems. So what we did is we just used the classifier that was trained on Kepler data, and we use it to classify the Kepler field of view that was observed by TESS. So then we can actually compare our probabilities there or compare our classifications. And we're currently in the process of that. We're doing, here you can see some example for sector 14. So on the bottom left, you see the Kepler light curve. On the top left, you see the TESS light curve. And for the Kepler light curve, we get a 95% probability that's a delta Scuti star, while for the TESS light curve, we get an 89% probability that's a delta Scuti star. And although the TESS probability is lower here, it's less certain. Also, the data quality, as you can see, is very different. So it's not as good as for Kepler data, clearly. But it's very interesting that in this case, it actually works, although our classifier was trained on a different space mission. So it's very nice here that we see for certain types of stars, we can just directly apply it, while for other types of stars, we actually realize that we need to start updating our training set with TESS data as well. So that's what we are doing now, is to make sure that we can actually take into account different systematics and instrumental effects that are present in the TESS data. Now, just in general, here you see probability as a kernel density estimate of the predicted probabilities. You see when we use our classifier and that is trained on Kepler data and apply it to TESS, we can see that the average predicted probabilities are all around like 0.3%. So the peaks are clearly there. While if you would use a classifier that was trained on the same data distribution, so apply Kepler trained classifier to Kepler data, it's actually more shifted towards the right, and it's shifted around 80%, for example. So this is really something because the data distributions are different. We see that it's not working as well for each of those stars, and therefore we are trying to develop some transfer learning methodologies as well to automate this process. And at the moment we are doing this by just updating our training set. Now, I now showed you how we are doing the supervised part to actually discover the high-level classes of variable stars. And now I will dive more into like the subclasses. So I will specifically go to the class of Gamma-Dor stars and Delta Scuti stars and actually see how we can distinguish the hybrid pulsators for those. So in order to do this, we developed a custom methodology that's actually based originally on the biomedical domain. So what we do here is we take the light curves and then we calculate something that is called the multiscale entropy, and this assesses the complexity. Now, this comes originally from the biomedical domain and was used to process ECG heart rate variability signals and to characterize them to distinguish different types of sick patients and healthy patients with different types of heart rates. And it seemed to work very well there. So therefore, we thought, okay, let's just adjust it and let's now apply this to light curve information, given that in some sense it's quite similar. And it seemed that it actually worked very well. So therefore, we went ahead and applied this to the problem of discovering subclusters of hybrid pulsators. So we take each of the light curves, we calculate the multiscale entropy, which is just some measure of the complexity and also represents the relative amount of short versus long-term variability that are present in data. And those curves consist of 10 data points, as you can see in the middle. And then we take those curves, so of 10 data points, and we reduce the dimensionality to 2 dimensions with something that is called UMAP, which is based on the topology of the data space. We specifically reduce it to 2 dimensions because otherwise we might have some issues with high dimensional spaces, and clustering algorithms usually work a lot better on lower dimensional spaces. So what we then get is something that is called on the right. We have 2 UMAP components that actually represent the 10-dimensional data space, but in 2 dimensions. And then afterwards, we run a clustering algorithm, specifically HDB scan, which is a hierarchical density-based algorithm. And then we actually get 2 clusters, as you can see, the red one and the purple one. And on the outskirts, these are orange. Those are not assigned, those stars are not assigned to any cluster because they are too far out. So the clustering algorithm sees them as noise, actually. So now diving a bit more into the multiscale entropy, as it says, as I said before, it actually assesses the complexity of a light curve. Now, how exactly does it do this? Well, we first take the light curve and we identify all the unique sequences that are present in the light curve. So what I mean is that if we start with the first unique sequence of length 2, so that's point x0 and x1, then we try to see how many times this unique sequence occurs. So we see x30 and x31 also occur. So that's a second time, and it's actually x60 and x61. So it's 3 times that the sequence occurs. And you see that there are some dashed arrows, and these are actually like error margin because it can fluctuate a bit. So everything that falls within these error margins, this can be seen as the same data point. So the first unique sequence, x0 and x1, actually occurs 3 times. And we then extend this sequence of length 2 to a sequence of length 3. So we then add x2 to our sequence. And we see that this one only occurs 2 times because the last point, x62, does no longer fall within this, within the confidence interval of the dashed line that is plotted here. And then we repeat this process for all other unique sequences, and we count how many times the sequence of length 2 occur and how many times the sequence of length 3 occur. You can choose any arbitrary number, but it's just always length of a sequence of length m and then the number of sequence of length m plus 1 that we do. And then we take the ratio of the sequence of length m divided by length m plus the number of times the sequence of length m plus 1 occur, and we take the natural logarithm of this. And this then represents the multiscale entropy. This then represents the sample entropy, because the multiscale entropy actually consists of 10 different data points, as I will show in the next slide. So each data point here on the right bottom plot is something that is called the sample entropy, and that's just the metric that I explained earlier. Sorry, I might not have been very clear on that before, but this is just the sample entropy, and the multiscale entropy consists of 10 different sample entropy values. And more specifically, what we actually do is we calculate a sample entropy value for different versions of the light curve. So on the top, you see the original version of the light curve. I think this was for the gamma DOR pulsator, if I'm not mistaken. And we calculate the sample entropy for this. So we get a point here on the right bottom, on the right plot, the first point, that is the first sample entropy value. And then we coarse grain the light curves. And what essentially doing this, we run a moving average filter with non-overlapping windows on this. And this actually removes the high frequency variability. So by doing this, we remove more and more high frequency variability, and we can calculate the sample entropy on different versions of the light curve. So you see, when we reach the bottom, all the high frequency variability is filtered out, and when we calculate the sample entropy value, it just calculates it on a totally different version of the light curve that only looks at the higher, lower frequencies in this case. And running this moving average filter is essentially equal to also increase it with an increasing Nyquist frequency. So in the original one, you see the Nyquist frequency is here around 260, while if we go to the bottom plot, and we have the light curve that is completely on the bottom, the Nyquist frequency is closer to 34 microhertz, for example. And by doing this, calculating the multiscale entropy, calculating the sample entropy for multiple versions of a light curve, we get the multiscale entropy, and this is something that really assesses the complexity, captures the full complexity spectrum of a light curve. Now, this multiscale entropy here on the left, you see on the bottom, you see each of the values of which it consists of at each scale. And then we see on the left, you see the frequencies from a Fourier spectrum, so an amplitude spectrum, and you can see there's actually a nice correlation between them. So that part of our multiscale entropy can also be correlated to the Fourier transform. Here you see some curves, some multiscale entropy curves for different variability types. So you see it for aperiodic stars, constant star, delta Scuti, and solar-like stars, and you can see that they are quite different. Especially the aperiodic one is very different. Then the constant stars, although it looks at first sight a bit the same, we see that constant stars always have a very, there's not a lot of standard deviation in the multiscale entropy curves for different types of constant stars, while for delta Scuti stars, it drops more sharply, and there's actually more changes in them. Now, going to the problem at hand, what we're really interested in is using it for gamma DORs and delta Scuti pulsators. So on the top, you see the example of a delta Scuti light curve, and then underneath you see a hybrid pulsator. And the hybrid pulsator is in this case more gamma DOR-like. So it actually takes the shape of a gamma DOR light curve, and it's actually in between that of a gamma DOR and a delta Scuti multiscale entropy curve, but closer to the gamma DOR, while the bottom one is also a hybrid, but this one is way closer to that of a delta Scuti star. So the multiscale entropy is actually able to represent the different continuum that exists between delta Scuti stars, hybrid stars, and gamma DOR stars, and even which one is the dominant type of variability here. Now, what we then did is we applied this to a catalog of known delta Scuti stars. So we calculated all the multiscale entropy curves for each of the stars in the catalog. And then we tried to we reduced the dimensionality to 2 dimensions, and then we clustered it with HDB scan. And we found that our methodology actually very strong at separating the hybrid pulsators from the pure delta Scuti stars in here. So on the left, you can see the delta Scuti stars in red, while on the right, you actually see the hybrid stars. And so the symbol shape, so it's a circle or a cross that actually indicates the labels that were assigned on a visual inspection by Bowman et al. But we did not really use this in our clustering itself. We only applied these labels afterwards to just visualize our results. And the colors is actually what we did, and that's based on the clustering algorithm HDB scan. And if we use that, we see that our algorithm is able to get an accuracy of about 82.5% for the delta Scuti stars, and about 80%, so 79% for the hybrid stars. So we can nicely distinguish between these two types of star in a completely unsupervised way. So we just clustered the data and then actually looked at some random samples that were present in each of the data. And then we identified, okay, these are hybrid pulsators, these are delta Scuti stars. And then we extrapolated this to the whole cluster. And afterwards, we compared it with the labels from Bowman et al. To actually see whether the results were correct or not. So we were sure that we could, that our methodology was behaving correctly. Now, afterwards, we did the same with gamma dwarf stars, and it also seemed to work very well. However, you can clearly see that the structure is more spread out in this case. You see that there's a lot more, so you first have a kind of an elongated shapes, and then the spread starts getting bigger and bigger. So there could be numerous reasons for that, which I will dive into afterwards. But first, we try to see, okay, is our methodology still working here? Specifically, this is the gamma dwarf catalog from Lee et al. But in the end, the goal is, of course, to apply this to the gamma dwarfs that are returned by our supervised test classifiers. What we'll do is we'll take those gamma dwarf stars and then run our methodology on that. But here we validate it based on an existing catalog, because then we could also check whether the labels were correct or not, of course. So we see that for gamma dwarf stars here, we can actually nicely identify them. This is the red cluster on the left, and we get about 87% accuracy. While for the hybrid pulsators, it's a bit more difficult. Here we only get 59%, and mostly because they're just so much more spread out. You see that there are some orange points here as well. Probably if those were included, so this is due to some issues with the clustering algorithm, or because it sees them as noise, we would actually increase the accuracy to about 65%, I guess, to 70% even. So it would be better, but still it's not as performant as in the delta Scuti case. So just really probe this to check, okay, now what can possibly explain this type of behavior, and why is it so much more spread out compared to the delta Scuti case? And what we then found is we coupled it actually with spectroscopy and also with the astrostatic rotation rates, because we know that most stars, because we know that rotation can actually shift the frequencies of gamma dwarf stars. And what we see is when we connect it to the V sin I values here on the left, that there is a very nice correlation between those two, and that actually the structure can be explained by the V sin I values, so by the surface rotation. So this is quite an interesting finding, to actually see that the rotation rate is so nicely correlated to or completely unsupervised data space that we developed here. And we then did the same thing on the right, and we did it for the near core rotation rates as well. We have some more data points here because we didn't have V sin I values for each of the stars in the sample. And we see the exact same correlation as well. So this is a very interesting point, because now we can also actually maybe use this information to try to predict, for example, the near core rotation rates based on their positions in such a diagram. We also built a regression model to see how correlated they were. And I think we got an R square of about like 60% or something. I would have to check the exact number. But it's very interesting that actually our data space can just capture the physical values that are present in the, so that can capture the physical values of the light curves. So now we really want to check with some more and other values as well, to see whether our data space can, whether we can find new physical insights based on this completely unsupervised methodology. Now, to conclude, we just used a supervised classifier for high-level variability classification, and then afterwards, we use unsupervised learning for the subclassification of pulsators. And the benefit here is that we also don't need any training set. We can just look at the clusters and then try to extrapolate what we find in one cluster to the whole cluster based on a sample of stars. And we can actually discover new classification and subclasses as well. And we are not bound by previous knowledge, because everything in a supervised case, you need labels, so we cannot predict anything for which we have not trained a classifier, while in the unsupervised case, it could actually just end up in a separate cluster. And the most important finding in this case, that actually the multiscale entropy and UMAP data space really contains physical information with regards to the rotation rates of stars. And this is very fundamental, because this means that with such techniques, we could potentially predict rotation rates, even though we never trained our algorithms for that. Especially if we combine it with spectroscopic value as well, we could uncover completely new relationships. And specifically, we really want to use this to discover the full interplay between rotation and multiperiodic pulsations. So thank you very much.
Thank you very much, Jeroen. We cannot give you a physical applause, but I'll give you one of these. If there are questions from the audience, please use the raise hand functionality or use a emoticon or emoji, whatever they're called, and I will call upon you. And while people are thinking of their first question, Jeroen, I will ask you something. So recently you've put a call out for some help from the community to manually classify some test light curves. And it got me wondering that so far the benchmark data set has been based on Kepler data, and as you mentioned, has very different systematics. So how do you expect that your results to change if, for example, you injected test systematics into your Kepler training set, or then compare that to, for example, a classification of actually test light curves? Is there going to be significant difference, do you think, in the ultimate confusion matrix from those two scenarios?
So I think, yeah, if you would inject if you would actually inject test systematics in that Kepler light curves, that might already be a difference. We will see that the confusion matrix will definitely drop a bit. But I think, yeah, because the real problem is in our test light curves, they're just so different. The quality is also different. We can have some more overlap, so we can have more combinations because the pixel sizes are different. So we can have types of light curves that are really just not represented at all in our current training set. So that will really give worse results, I guess. However, if we are really able to take and keep on updating our training set to incorporate all these different types of systematics, I think we should actually be able to achieve a similar accuracy, I guess. Because currently when we run it for certain types, as I said, for like delta Scuti stars, because it's so the frequencies are so high, we can actually very nicely see it. And also for gamma dot stars, the results are quite fine. It's really when we have certain characteristics that could be confused with binary systems in this case, then the classifier completely messes up. And it might sometimes be difficult to fully inject these into the test data, into Kepler light curves, because we might not know all of them. There might be some unknown characteristics as well that we cannot inject there. However, I think it would definitely already make the results better if we inject these in the Kepler light curves to then, but then it might in the end not be worth all the effort to inject these if we can just update the training set.
Mm-hmm. Questions from the audience?
So if anyone is interested as well in helping out with doing some vetting for the pulsating stars, definitely let me know. Always welcome to join the team. We're always looking for more people on that front.
Jeroen, Dominic, can I ask a question? I cannot raise my hand.
Yes, please go ahead, Rita.
Yeah, I was wondering. I mean, I'm of course very much intrigued by this. The fact that you could actually infer some correlation with rotation with your UMAPs indexes. I was wondering if you could tell us more about these two indexes and why do you think that they would correlate with rotation, and what's the explanation behind it?
Yeah. So, I mean, so the UMAP components are actually just a two-dimensional representation of the multiscale entropy. So it's actually it just represents the multiscale entropy, but in 2 dimensions. And the reason why we do it why we compress it to 2 dimensions is because it's easier to visualize for us, and also the clustering algorithm just works better if you only have 2 dimensions. But so it's in essence this means is we have a correlation between the multiscale entropy and the near core rotation rates in this case, and we just use UMAP to visualize it and to actually better understand how that is working. And probably what the reason for this is probably because rotation can shift the frequencies of gamma dot stars shifts the frequencies of gamma dot stars to I think higher levels, if I'm not mistaken, and the opposite for delta Scuti stars, and therefore we can actually find some correlation in there. But it's really, I think it's just the start that we found this correlation. Now, I think the next level is try to exploit this and see whether we can actually build a predictive model based on that, and see if we feed it the multiscale entropy and as input, can we actually predict the rotation rate for all these different stars? Although we found a correlation, would be very interesting to know what is the accuracy if we train such a model with multiscale entropy values as input and near core rotation rates or V sine I values as output, and see how accurate our model is in that case. I think it's probably because it's our model, or the multiscale entropy captures different types of variability, and this capture the different types of like low versus high frequency variability, and therefore it can capture some kind of the rotation rate, because it can actually shift the frequencies of the stars.
Okay, thank you. Interesting.
So Joyce Guzek has asked in the chat if you need help with Delta Scuti Gamma Dor star classifying, and I think the answer is yes.
Yeah, indeed. So we are currently, for vetting, we are doing all types of all types of variability classes, but again, so any type of variability class where you want to help to classify those is always welcome.
Savita, please go ahead.
Yes, hi. Thanks for this very interesting talk. I learned a lot of things. Yeah, about this, the multiscale entropy, since you were talking about rotation, but core rotation, I was wondering if you can use it for other types of classification. I'm thinking about surface rotation, for instance, because you also have this modulation, and can it tell you if you have differential rotation or things like this? Do you think we can use it for this, or?
I think it might definitely be a possibility. We first need to like do some more research, I guess, and see how exactly that shifts as well. But because we also find a correlation with the V sine I think for different types of rotation, it might actually work as well. But now it was specifically was for gamma Dor stars that it was working very well, and their hybrid components, because there we know that rotation can actually impact the frequencies. So it might depend on the underlying variability type as well, whether we can use it or not. But I think it's definitely worth to explore more and to see for which type of rotation and for which variability types we can actually measure that.
Okay, maybe I'll contact you then to see how we can do this.
Yeah, perfect. I would be very interested in that.
I guess there's a lot of applications here, Jeroen, because you've only applied this to the hybrid pulsator classes of the Gamma Dor and Delta Scuti, but different types of spot modulation in cool stars, for example, is another application. Have you thought about things like that as well, differentiating those?
Exactly. Well, I haven't thought about it, or I haven't started applying it to that, but it's definitely on the to-do list, and it's something that should actually be done to see how well it works for those types of stars as well. Or those types of rotation, because now, I mean, it's just on one type of star. Now we want to know whether you can generalize it to cool stars as well, and their spots, for example. It would be a really interesting case, and I think that it might actually be possible to apply to that, because also it's a very characteristic type of rotation that we can see in the light curves. So the multiscale entropy, maybe we fine-tune it a little bit, might work on that as well. But I have not actually applied it myself to that. But it's definitely, we should definitely try that.
Any other questions for Jeroen?
Yeah, Jeroen, have you do you have plans to apply these algorithms to Plato simulation data? And is that a possible outcome for your work to use it in the context of the Plato complementary science?
I think that's definitely definitely a goal, because I mean because for our task classifications, for example, the whole methodology, we could actually probably use it, or we could use it to inform the Plato classifications for that as well. So if we have the models and stuff, I think we could definitely do it for Plato. I don't have any concrete plans to start on applying it, but the methodologies itself, they should definitely be applicable. I don't know whether I will be able to do that before the end of my PhD though. But I think the methodology itself is applicable to Plato, and we should actually explore that as well, because one of the goals why I'm working also with this unsupervised part is because it should be independent of mission characteristics. So the benefit here is it doesn't matter whether there are test systematics or Kepler systematics. I mean, it just relies on the data space for this unsupervised part of the methodology. So we only look at that, and if we just apply it to another data space, then it should still be able to distinguish these different types of stars, irrespective of the characteristics. So for Plato, that would definitely be worth to actually look into that.
Last chance for questions from the audience. Okay, I don't see any other hands or smiley faces, so I'll close the question session there, and thank you very much, Jeroen, for your very interesting talk. And one of our goals here with Good Vibrations is to allow finishing PhD students to advertise themselves, and he's done that excellently by saying that he needs a postdoc to work on Plato data. So if you are someone who would like to talk to Jeroen about his future, then please get in touch with him. And thank you very much, Jeroen, once again. And I'll pass back to Rita just in case she has any other announcements.
Thank you.
Nothing to add. Thanks a lot, Dominic, and thank you very much, Jeroen, for a very nice talk. And see you soon. I wish, and have a good day, night, whatever. Bye bye. Thanks a lot.
Thanks,
Thank you.
everyone.